Hey, so welcome to today's class. We're going to be studying the mean value theorem and monotonicity. Before we get there, just a review exercise from what we were studying before. Here's some classwork. Find the extreme values of y equals 2 times the square root of x squared plus 1 minus x on the interval 0 to 2. Okay, so I'm going to solve this, but I encourage you to do it first, so please pause it and solve it yourself, and then press play when you're ready to see the solution. Okay, first find the critical points. Okay, so take the derivative. You have to use chain rule here. Alrighty, so let's simplify things. This will end up becoming 2 and 1/2 cancel. So 2x over the square root of x squared plus 1 minus 1. Okay. And the thing you might want to do is get a common denominator. So multiply this 1 by root x squared plus 1 over root x squared plus 1. That'll end up giving you this function. Okay. And then two things. So you can find out where that derivative equals 0. That's going to be whenever the top equals 0. Okay, so trying to isolate x, I'd recommend adding over, well actually, wait. Let's see, sorry about that. I would recommend adding over the root x squared plus 1. And then I would square both sides. That leaves you with, if you subtract x squared from both sides, 3x squared is equal to 1. X squared equals a third. X equals plus or minus root 1 over 3. Then you would set the bottom equal to 0, but at the bottom, since it's x squared plus 1, it's a positive plus a positive 1. It's always positive. So the bottom will never equal 0, and this will never not exist. So now your candidates that you will test, you'll only take the positive of those critical points because we're on the interval 0 to 2. So we'll take positive root 1/3 or 1 over root 3. And we'll take 0 and 2. Okay, so if you plug in 1 over root 3 into that original equation, you get y equals 2 times the square root of 1 over root 3 squared is just a third, plus 1 minus 1 over root 3. This gives you 2 root 4/3 minus 1 over root 3. So that first radical will simply, the 4 will come out to a 2, so you get 4. So square root of 4 is 2 times 2 is 4 over root 3 minus 1 over root 3, which is just 3 over root 3. And when you rationalize it, you end up getting just root 3. If you plug in 0 to that original equation, you get 2 times square root of 0 squared plus 1. That's just 2 times square root of 1 is 1. 1 times 2. 2 minus 0 is 2. And then if you plug in 2, plug in 2 okay, 2 root x squared plus 1 minus x. That's 2 root 5 minus 2. 2 times root 5 minus 1. Okay. And let's see, what can you say? 2 times root 5 minus 1. Maybe a good idea in this case to get a good calculator approximation. So this one is about 2.472, and the root 3 is about 1.71. So you see you have your max, you have your min of 1.71 and your max of 2.472. Okay, so anyway, the topic for today's class is focusing first and foremost on something called the mean value theorem, abbreviated MVT. You can think of it like this. If we have some function over here that looks, let's say, just like a parabola, we would be interested in figuring out when is the function increasing and when is the function decreasing. So you can already tell that, well, right there at C you have a local maximum. If you look at the curve up to C, you can see that all the tangent lines are positive. At C, the tangent line hits 0, and then the tangent lines start becoming negative and more negative. So we see that positive tangent slopes are associated with an increasing function, negative with a decreasing function. So we'll get into more of that soon. The mean value theorem says that if f of x is continuous on the closed interval a to b and differentiable, just means you can take the derivative, on the open interval a to b, comma, then there exists at least one C in AB open such that we have this statement true. F prime of C is equal to FB minus FA over B minus A. So if we think about it, you can imagine, let's just say some function. And let's say we wanted to consider the function on this interval. Alright, so this is the point A, f of A. This is B, f of B. Well then, if we want to know the tangent of that secant line that connects the two of them, We get it by taking FB minus FA over B minus A. That's our formula. So this theorem is saying that there must be one point, at least, such that we could take our green line in this case and just push it up, and you'd actually find there's a point on the curve itself. So this is the point C, where f prime of C equals the slope formed between the two endpoints. So nothing too wild here. There is a proof for it if you'd like to look at it. That's on page 231. I encourage you to check that out. Okay. So an example, let's do this. Let's verify the mean value theorem for fx is equal to root x on this interval 1, 9. So we want to verify it. That means, well, the theorem says if it's continuous in AB, differential on open AB, then there's at least one C in AB such that the derivative equals the slope between the endpoints. So let's find the derivative. That's 1/2 x to the minus 1/2, or equivalently 1 over 2 root x. What do we want that equal to? Well, we want it equal to the slope between the two endpoints. So what would that be? That slope would be square root 9, that's f of 9, minus square root 1 over 9 minus 1. So that turns out to 3 minus 1 over 8, or 2 over 8, which is a fourth. So then the question is, now bring it to what we know on the derivative, what do we need to do? We find out when f prime of x is equal to 1 over 2x equal to 1/4. Okay, and so in doing this, you'd solve, you could cross multiply. 4 equals 2 root x. Okay, then as you solve, you'll divide both sides by 2. Leaves you with 2 equals root x. To get x by itself, you square both sides. So 4 equals x is a critical point. Notice that based on our function of the derivative, there is a place. Oh wait, no, never mind. I was going to say something else about some critical points, but what we just did is we tried to find a place where the derivative is equal to the slope of the secant line. So now we know. At x equals 4, the slope is 1/4. Okay. So we're going to talk about increasing and decreasing behavior. So let's write that out. Increasing, decreasing, like going up or going down. That's what we mean here. Getting to bigger y values or to smaller y values. So we say this. F of x is increasing on AB if fx1 is less than f of x2 for all x1, x2 in this interval a comma b, such that the first one is less than the second. So all it's saying is that if you looked at an interval and picked 2 points in that interval, that the function value of the second is bigger than the first, as long as the second x value comes after the first one. So that's what increasing means. Decreasing if opposite fx1 is greater than fx2 for all x1, x2 okay. And now for this word, monotonic. We say that f of x is monotonic, like one tone, monotonic on some open interval a comma b if it is either increasing or decreasing on AB. Okay, so let's get a theorem. Let f be differentiable on AB. Okay, so if the derivative is greater than 0 for all x in AB, then f is increasing. So whenever the derivative is positive, a function is increasing. And then the opposite is true. If the derivative is negative for all x in the interval, then f is decreasing. Okay, so now in order to prove this kind of statement, we'll end up using our mean value theorem. So let's have a look. Proof. Let's start with the if statement on top. Suppose that f prime x is greater than 0 for all x in some interval. Well, the NVT tells us that for any two points, x1 and x2, in this interval, there exists a C between them such that it's a mean value theorem, right? We just said the mean value theorem tells us that for any 2 points, x1 and x2, there's a C value such that fx2 minus fx1 over x2 minus x1 is equal to f prime of C. Right, there's some value where the slope of the tangent equals the derivative of the endpoints of an interval. Well, then now it's just a matter of being a little clever. So we're trying to show that f of x2 is greater than f of x1. So here's what we'll do. We're going to move over the x2 minus x1. So multiply it over, you're left with fx2 minus fx1, which is equal to f prime c x2 minus x1. Well, think about this. You know that x2 is greater than x1, so that one's positive. F prime of c, let's see. Okay, let's think about this statement. Since in our proof initial statement we supposed that the derivative is always positive, then the derivative here, f prime of c, must always be positive. But there's more. Since x2 always comes after x1, x2 is greater than x1, and that can be written as, that's going to be a positive number, just like f prime of c is. So positive times positive is a positive. In any case, it's greater than 0. So that tells us, by rewriting a little bit, that fx2 minus fx1 is greater than 0. Well, doesn't take much to add over fx1. Okay? So what we just showed is that f of x2 is greater than f of x1. But wait a second. Oops. That's what we said for our definition of increasing. Right, we said if the second function value is greater than the first, that's what we have here. fx2 is greater than fx1. That is QED. And so just to illustrate a little bit of this, if you imagine some curve like this, draw some tangent lines in just to get some perspective. Notice that there's nothing here that was negative. And since the slopes are just getting steeper and steeper, yeah. So we have that for this one, the f prime x is always greater than 0 for that upward tending function. And if it were downward tending, then we would say that's decreasing, so f prime of x must be negative. And even with this one, you can see the negative tangent lines going off of this guy. So hopefully that's a good visual for you. Let's work a analytical example. Show that ln x is increasing. Okay. That's y equals ln x. Well, we'll need the derivative. So at the top equals 0, there's no solution. So at the bottom equals 0. So y prime would do not exist at x equals 0. And the domain for log, I'll write it in interval notation, negative infinity, 0, 0 to infinity. Oh, excuse me. The domain is only the positive part. The domain of zero to infinity. 0 to infinity. And fix that. Okay. So the whole domain is only 0 to infinity, and the only critical point would be at 0, which is not on that domain. So then you can look and see, well, since the domain is all positive numbers, and since the derivative is just 1 over x, well, then the derivative is always positive. Okay, and thus y equals ln x is increasing on 0 to infinity. Okay, last example for this class, and then I'll let you go. So this problem, find intervals on which this function f of x equals x squared minus 2x minus 3 is monotonic Okay. Again, monotonic, that's going to be the stretches where it's just increasing or just decreasing. Okay, so you take the derivative. That'll factor out nicely. Z equals 0. So x equals 1 is a critical point. And just looking at the function, so it's already factored here, 2x minus 1. Well, if you put in any number greater than 1, it's going to be a positive derivative, so it's increasing. If you put in any number smaller than 1, it'll be negative and decreasing. So we say it like this. We say f prime x is greater than 0 when x is greater than 1. Derivative is less than 0 when x is less than 1. So f is increasing on this interval and is decreasing on this interval. So if you just remember that whenever we find that the derivative is positive, then that's where the function is increasing, and if you ever find that it's negative, that's where the function is decreasing. So homework for this section I will post on Moodle. And if you have any questions, bring them in to me next week as soon as you can. Alrighty, God bless.